In this segment, we'll discuss general design principles for databases, including normalization, which is a formal term for well-organized database design. Knowing how to create tables, declare column types, represent enumerations, and set up indexes and keys is all important, but it still doesn't tell you how to design a database, how to decide which tables to create, with what columns, when to arrange foreign key relationships, and so forth. Database design, like any other kind of software design, is an art, and it requires experience to do well, but there are some important design concepts and good rules of thumb that will help. We'll go over those concepts in this lecture, but before we do, let's talk a bit about what we're trying to accomplish in a database design in the first place. What makes one arrangement of tables, columns, and so forth better than another? Well, it turns out that the criteria for good database design are the same as for other good software design. In particular, good database design, 1, makes it hard to screw things up. A good design minimizes the opportunity for human error, such as incorrect modifications of code or data. And 2, a good design is easy to understand. Good design hangs together well conceptually and allows people to think about one part of the database without having to keep all the rest of it in mind. And 3rd, a good design is easy to modify. Good design adapts readily to changes. It doesn't require revisions of large parts of the database to make a small change. And then 4th, a good design is resource efficient. Good design is fast where it needs to be, but doesn't add complexity to gain speed where it's not needed. So, here are basic design rules in support of those 4 goals. So let's start with rules that make it so that it's hard to screw up. Databases, like all software, are complex, and anything you can do to minimize human error helps. So 3 good examples are: first, use the most restrictive column type possible. We mentioned earlier that an unsigned integer, for instance, is most useful not for efficiency, but for reliability. Using unsigned ints to hold values that should not be negative, like a count of courses taken or a line item number, eliminates the human error of entering a negative value. Declaring a varchar with just the maximum space needed and nothing more precludes accidental entry of too large strings. And using a date field instead of a varchar with date-like string contents ensures that only valid dates are entered. Also, declaring a column not null when its data is mandatory prevents accidental omission of that data. Choose your column types carefully with special concern for preventing human data entry errors. Next point, add unique keys to enforce uniqueness. Add UK constraints on columns or sets of columns to ensure uniqueness when relevant. Examples might include the combination of street name and number for a table of buildings, or a department name and course number for a table of courses. And 3rd point, under this general category, DRY. Now, if you haven't encountered the software design acronym DRY before, it stands for Don't Repeat Yourself, and it's usually pronounced just dry. Good software design avoids repetition of code or data, for instance, by factoring repeated code into functions, and by creating one copy of data and referring to that one copy from other locations as needed. This is partly for efficiency, but more importantly, because multiple copies of the same code or data invite incomplete modification of the data. For instance, imagine that Bakery 3 added a column customer email to receipt and copied a customer's email into every receipt for that customer. Modification of a customer's email would then require changing every instance of it within receipt, and one or more instances might be missed. If the email is instead put into customer, linked from receipt, then only one copy exists to be modified. Okay, moving on to the second major category here. Good design is easy to understand. And to that end, first of all, make each table represent a conceptually clear and single thing. In the bakery databases, customers, receipts, line items, products, ratings, etc. are distinct entities. Jamming customer data into receipt or product flavor and kind into rating would both violate the dry standard we just talked about, as the same data might be repeated many times, and would muddy the purpose of each table. Number 2, name consistently, and clearly for that matter. We'll add that in. Name tables, columns, and constraints carefully and consistently. Using a variety of wording and terms is often good style in non-technical prose, but it's a sin in variable naming. All of Bakery 3's table names, for instance, are capitalized, and all are singular words by convention. Unless there's a more meaningful name, join tables are called Table 1 x Table 2, with Table 1 the first in alphabetic order. That makes them predictable. So it's product, not product with a lowercase p or products, and it's discount x product, not product x discount or discount for product. All column names are lower camel case. All the generated primary keys are named ID, and all the foreign keys are named parent table, whatever that may be, ID. Again, predictable. And good naming is more than following a convention. Pick meaningful, precise names, not vague ones. Receipt, for instance, is clearer than purchase. Product is clearer than item. Purchase date is clearer than timestamp. When choosing a name, come up with several possibilities and use the best one you think of rather than just using the first one that comes to mind. And a special note, by the way, if you develop in Windows, which is case insensitive, you'll find that you can get away with using product with a lowercase p or even all caps product if the table is actually named capital P product and the rest is lowercase. Don't rely on this. All your SQL will break when you move to a Unix system, if you do. Question 1. One column in Bakery 3 really doesn't live up to the clarity standard. Which one would you say needs improvement, and suggest a better name? So, highlighting that so we can see it. It is a bit of a judgment call, but in my opinion, product.kind is pretty ambiguous. Kind, what does that mean? Pastry type, perhaps, or something similar would have been better. Okay, next major category, good design is easy to modify. And here we finally get to this normalization concept as the first rule of thumb under this category. Database normalization is a formal mathematical concept involving the organization of database tables and columns. Normalization has many roles in database design analysis, but its most important purpose really is to enforce modifiable and flexible design. Normalization is defined in relational algebraic terms, so we won't go into the formal definition here. But an informal discussion of what it means to put a database in normal form is useful, and three rules in particular stand out. The first is one value per column. One of the most basic normalization rules is that a column should have one value. Putting a list of values into a single column, for instance by concatenating a series of strings together into a single varchar, is hard to maintain and search. If you're tempted to cram a list of values into one column in a table A, then create instead a separate table B of the values in question, with a foreign key relationship from B to A, so that each row in A may have many associated rows in B. And if the same B value might also be associated with multiple rows of A in the other direction, then create a join table and an N-to-M relationship. So question 2. Once again, one column in Bakery clearly violates this standard. Which one, and how would we fix it? And the answer really is that customer.favorites lists a set of products all crammed into one string, right? Violating the one value per column rule. A better solution would be a join table linking customer and product in a N-to-M relationship showing which customers favor which products. And the next rule in normalization. Tables shouldn't look like joins. You've seen enough join outputs by now to recognize the pattern. The columns fall into two or more groups, with a good bit of repetition within each group due to the Cartesian product behavior of a join. Consider a table like the following one here with some sample contents. We've got a create table street, and we have city name and then street name and number of lanes for the street. And here's some data. The city names are repeated. It kind of looks like a join, really. This table should be broken into a city table holding 2 cities in our example, Westmont and Lincoln, and a street table with 4 streets in our example. It would link the 2 tables via a street.cityID foreign key pointing to a cityID primary key. This way, the name and possibly other data for each city is repeated just once in one row of the city table. So, question 3. Consider the table below here, which is meant to represent a book that might be on loan at a library. Now, how would you break it up per the conversation above? How many tables would result? And the answer should be more than 2. There really are at least 3 different concepts here, and they need at least 3 tables. Books are an independent concept, so a book table and a separate loan table would make sense. Also, borrower information would be repeated many times if the same borrower borrows many books, and borrower is a 3rd independent entity deserving its own table. Each row in loan should have foreign key links to the relevant book and borrower, so the right create table statements would be something like this. We'd have a create table book, and it has just the book information, as you can see, and a primary key we've added to it. A create table borrower with just borrower information, name and card number, and then one for loan with foreign keys to the book and borrower involved. And then question 4. We really should have created a 4th table in this example, and a join table to go with it. You might already have done so in your solution, but if you didn't, think about what 4th table should be broken out of book, and why is a join table in order? So what you should come up with here is that an author table would be a good idea. Multiple books may have the same author, and the existence of that optional second author field here, column, suggests or reminds us that a book may have several authors. One wonders what the original design did with the 3rd and later authors, if there were that many. Now, this strongly suggests we create an author table with an author x book join table to prevent an n-to-m relation between book and author. We could then represent as many authors per book as needed, not just 2 of them. So we'd have create table author with just the name, and then this author by book join table to link together authors and books. A final normalization rule is to eliminate obligatory nulls, also called temporary nulls. For instance, what would the book and loan table contain if we wanted to record a book but it was not currently on loan? We can't just remove the book entirely from the library database. The unavoidable alternative is to insert a row in book and loan with nulls for borrower name and when due and so forth. So running back up here, we'd have to null out this stuff because nobody's got the book on loan, but we got to have the book in the database. And that's why those fields were left nullable in book and loan. But this is awkward, and the fact that we're obligated to create null values suggests that we should have just stored the book information in one table and made loan and borrower tables to link to it. Note, for instance, that those same fields are not null in the solution table, since we won't have rows in those tables unless there's data to fill them. So not null here, and likewise not null for when due. So question 5. A similar obligatory null appears in the book table in answer 3, and again suggests the need for a separate table, one we just created, in fact. Where is this obligatory null? The answer is that the second author name is nullable since there might be no second author. The original design with its 2 columns for authors eliminates the possibility of a third and makes one of them usually an obligatory null. And the n by m solution from answer 4 allows unlimited numbers of authors and requires no nulls. This author name and second author name kind of half-baked join is common in bad database design. You'll even see things like third author name and fourth author name jammed into a book table, and they're almost always left null. This pattern is almost always a design mistake and should be replaced with a join. Our final database design point is that good database design is resource efficient, both in time and space. And some rules of thumb in support of that. First, add indexes. Well, we've already mentioned adding indexes to prevent data entry error, but of course you should also add them on any field on which you often expect to hunt for values. Absent an index, you cause a search through the entire table, which, given the large size of many database tables and the slowness of disk access, can be prohibitively time-consuming. Just a brief question 6. If a table has 1,000,000 rows and you must search through all of them, assuming one row can be fetched per millisecond, how long does the search take? The answer is 1,000 seconds, around 20 minutes. In question 7, suggest an index on the borrower table from answer 3 that would probably be useful given typical book check-in and check-out procedures at a library. The answer is that we could probably use an index on card num. A library card number is the chief way to identify a borrower in most library procedures. But as we noted when introducing them in an earlier lecture, indexes are space expensive and can even take more room than the table data itself. An index on borrower name, for instance, would probably be a waste since name doesn't uniquely identify a borrower anyway, and name is not the starting point in the check-in and check-out procedure. Though now you might understand why a borrower asking if their records can be looked up by their name instead of by a card number might be told, sorry, the system can't do that. And while we're at it, let me slip in an extra note here too for join tables. The 2 foreign key columns that such a table must have will also suffice jointly as a primary key if you require one. So don't add int or ID int primary key columns to join tables. And then the final point, use the most efficient type. Now the earlier lengthy coverage of types discussed size trade-offs ad nauseum, so we won't repeat them here. Just remember that column size does matter, and you should think about this when you declare columns, especially for large tables. So here's a checklist that summarizes the design ideas that we've discussed. First, avoid human error by selecting the most restrictive column type possible and by adding unique keys and not null restrictions. 2. DRY. If one piece of data appears in multiple places, refactor the design so that it appears only once in the database. 3. All tables should represent conceptually clear single concepts. 4. Name tables and columns consistently and clearly. Come up with several name possibilities and then choose the clearest. 5. If a table looks like the result of a join, then it probably should be. Break it into 2 linked tables. 6. Avoid obligatory nulls, cases where you have to accommodate the possibility that data is not available when it should in fact have been put in a different table, and omit the row if the data is not available. 7. Add indexes where needed but not otherwise, and in particular don't add int primary keys to join tables. And then 8, use the most space efficient column type. And while we're checklisting here, some naming style rules, a summary of all the ones we've mentioned so far, plus a few minor extra items. And this will help make your design consistent. Also, following them is important to passing the IHS exercises for the course, since IHS expects these naming conventions. So first, table names in upper camel case. Probably should put the capital C there to emphasize that. That's a singular form also, describing one row. So product, line item, so forth. Join tables are named Table A cross Table B, or X Table B, with tables in alphabetic order, unless a more meaningful name is available. Number 2, column names in lower camel case, and foreign key names in the form parent table followed by ID with a lowercase d. So, for instance, receipt ID. Number 3, unique keys in form UK and then one or more columns separated with underscores. So, for instance, UK flavor underscore kind. And in addition, the columns must appear in the name and in the index in alphabetic order, unless there's some compelling reason not to do that. Number 4, non-unique indexes or keys in the same form as unique keys, but with IN prefix instead of UK. And then foreign keys in the form FK table name and then the columns, adding the table name after FK so that FK names are unique across the entire database.